Hello everyone, welcome to this tutorial 2. In this tutorial we will look at assignments problems regarding point groups and phase groups as well as the stereographic projections. So I hope you would have seen in the lecture couple of lectures pertaining to these chapters detailing the procedures of obtaining a particular stereographic projections as well as talking about a zonal relationships. So what we will do today, we will just look at, suppose if you are given n number of poles, how to find out the zone axis, which is very simple. Nevertheless, we will just solve some of the problems and then I will just show in a stereographic projection which I will draw on the board to easily find out how to look at this zone axis pertaining to different poles. Suppose if I have poles represented by, for example, H1, K1, L1, H2, K2, L2, H3, K3, L3, etc. So all of them will belong to a zone called U, V, W, right. In the lectures this is what is shown. All those zones will belong to, all those poles will belong to particular zone. So you can write something like this. This is zone, also called the zone axis, and this is called Weiss zone law. You would have seen that. Let us call it as zonal relationships. We will now go through general idea about this finding out the zone axis for given number of poles. We will also try to put it in the form of a stereogram. What I am going to do is, which you already know, I am going to draw a 0, 0, 1 projection, and then I am trying to find out all the poles which can be identified from this stereogram, and then we will just look at how this zone law can be directly visualized from this, or you can just also try with for a given number of poles how to find out the zone axis. So that is what I am going to just demonstrate, which is already clearly and nicely demonstrated in the lecture, but nevertheless if you are given some arbitrary numbers, how to go about it with the help of stereogram. This is what I am just going to demonstrate in this tutorial class first. So what I have drawn here is a standard 001 projection, stereographic projection, and then all the poles I have marked as a standard one, which you all know. So, now how to find out the zonal relationship between these two according to this. Suppose if you have u, v, w as a zone axis, then all h1, k1, l1, h2, k2, l2, etc., will be 90° towards this pole according to this equation, right. These two is simply, if you consider these as a 2 vector, and this is a relationship. So, that is a very simple idea. So, for example, if you take this 0, 1, bar 1, 1 as considered as a zone axis, and then you have from the stereographic projection, you all know that stereographic projection is the angle true projection. So, this from center to here it is about 90°. So, 45 approximately, and then you can just have a rough idea about the angle here. Then you see that it will be some, for this kind of a pole, if you see somewhere the 90°, you will find this is the great circle, and whatever it is falling on this pole will be the corresponding poles of this zone axis. So, similarly, you have this zone axis 001 zone axis, and you have all this poles which is falling on this projection will form a poles. So, this is a zone axis 001 zone axis, and these are all its poles. So, if you choose to check whether they obey this Weiss zone law, you take any one of the dot product of this, either 0 bar 1 0 dot 001 will be 0. You take any one of this, it will obey this law. So, that is the idea of finding out the zone zone axis for a given poles, or for a given poles to identify the zone axis. This is the way to do it. You can also identify some of the other important aspects. I will just draw few more poles here. So, it becomes a little more clumsy, but nevertheless it is a cubic system. Remember, only in cubic system your all the plane normals are perpendicular to the plane itself. That is a very highly symmetrical nature. So, it is very straightforward to get into this kind of an analysis compared to other crystal systems. So, you can see that you can simply identify the for a given zone what kind of poles will fall onto the great circle, or the vice versa. Okay. So, now I will write some more zonal relationship. Suppose if you consider h dash, k dash, l dash belong to the same zone axis. Suppose if you find some other, apart from this, some other pole also belong to this zone axis, then that also will follow this rule. like I said, if you go through this, if you have these kind of relationship also will be valid, and you can, from this stereogram you can simply look at this kind of relationship. For example, if you add these two, for example here 0 1 bar 1, 0 1 bar 1 and 0 bar 1 1, 0 bar 1 0, sorry 0 0 bar 1 1 is here and 1 1 bar 0 is here. So, if you add these two, this comes. So, you can check with this also, if you even add these two, the same thing will come. Similarly, you can find this by adding these two or these two. For example, if you add these two, bar 1 and 2 bar and 1. So, 1 bar 2 bar 1. So, like that you can keep on generating this pole by this kind of relation. So, since it is highly symmetrical, it is very easy to find out these kind of poles. I will just give you one more a clear example. Suppose if you have this kind of direction or a pole, how to identify this in this stereogram. So, if you look at this, you can write 1 2 3 in terms of 1 0 1 plus 0 2 2, which is nothing but 1 0 1 plus, similarly 1 2 3 can also be written as NH NK NL dot U V W is also equal to 0. So, you see now the simple zonal relationship we are now extending to its family of directions or planes, something like this. So, this you can show it on this stereograph with, probably I will take another color chalk to distinguish, already the figure is clumsy. So, to show this 1 2 3 pole, what is that you have to do? So, it is combination of 0 1 1 and 1 0 1. So, let us look at this 0 1 0 and 0 1 1. So, we have to draw a great circle which pass through these two. Let us see how it comes. So, which is nothing but this pole again, which we have already drawn. So, it is easy. The other one is bar 1 0 1 plus 1 1 1. So, bar 1 0 1 is here and the 1 1 1 is here. So, we have to connect these two. So, now you see I have connected according to these two additions, two great circles I have drawn. If you look at this intersection, which is nothing but 1 2 3. So, this is how you should visualize this kind of relationship on the stereogram, how to look at this kind of poles which is intersecting on this simple stereogram. So, you have the zonal relationship. So, these also will fall into this category. So, I think I'll stop here with the zone axis problem. So, I hope now all of you will be able to solve this problem. If I give you quite a bit of poles of different sign. You do not have to worry about it, simply look at this relation, draw a stereogram, and wherever you are trying to find the particular zone and its poles which is having this relationship, simply you try to draw this and then find out the corresponding zone axis or the poles vice versa. So next I will move on to some problem on point groups and space groups based on this stereogram. Suppose if I ask you to draw a stereographic representation of point group 2, 3 and 2 bar. So, how to go about it? So, you know that 2 means a rotation. So, you can have a reference like this. So, let me first look at this 2 point group. For point group 2, that means you are having the rotation axis along the y. Suppose this is just shown on the stereographic projection. Suppose if you have a point here, if I do C2, that is rotation of 180 degree. If I rotate like this, so it will go to the other end, but at a different level. So, this is on the top and this will go at the bottom. If I rotate 180 degree, that will go to a bottom, but at a different level, not at the same level. Suppose if I have a rotation point group from the top, then I will produce equivalent number of positions like this. So, C3 is 120. So, it will produce equivalent points at these positions, but at the same level. So, what is 2 bar? 2 bar is equivalent to a mirror, but then still it is 2 bar is roto inverted. So, that is the symbol 2 bar. So, how to draw this? So, what I have done here is a C2 with a mirror. So, mirror is when you have a sorry, it is a mirror, but it is a roto inverter. So, what happens when you rotate? So, this will go there, it will invert. So, that will come up. So, that is what it is, it is all in the same level. So, you have the mirror which is cutting this plane. Similarly, I will show some more examples. So, what I have done here is 3 bar, that means roto inverter. Suppose if I start from this point 1, it will go, it is 120 degree here because it is C3, but it will also invert. So, invert means it has to go through the center. So, it goes here and 120 invert, again 120 invert, 120 invert, 120 invert. So, like that it will keep on producing the equivalent points. So, this is at one level, this is at the different level. So, you can just follow this kind of notation to follow. So, it will follow that sequence. This is for, so you can say that simple rotor a simple rotor will produce 3 equivalent points, but with an inverter it will produce 6 points. So, that is the idea you have to remember. So, let us go to some little more examples with we will combine a mirror with a rotor. For example, the point group 2m. So, what will happen to this point if you have 2m? That means this is a two-fold rotation in the z axis. So, you have 2 mirrors, one is here and another mirror is here. So, what will happen now? Suppose if I do 180 it will come here, but it will reflect. So, it has to come here, right. So, since you have a mirror here, this will also reflect here. Since you have then again 180, it will come here, but it will reflect here. So, 2 mirrors. So, this will also reflect here because you have the mirror here. So, a 2 bar M produces 4 equivalent points with the 2 perpendicular mirror here. I repeat, suppose this is my starting point, 180, reflect, 2, rotation, 3, again this is 4, something like this. Okay. So, you just do this, it will be obvious. So, you can just try the sequence at any order you can try, but all that you have to realize is this mirror will repeat and this mirror also will repeat. So, there is a 2M, that is a point group 2M, sorry 2M, a combination of rotor plus mirror. So, we can try one more example. So, what you find from this kind of a point group, this is just a note, when you so, when you combine 2 symmetry elements, a third symmetry element is automatically generated. So, that is why it could be also called as 2M. So, we are trying only 2M, but it produces equivalent positions like 2MM. So, that is why this sentence. So, let us try now 4MM point group. So, it will be like this. So, you have the C4 rotation axis on the z axis. So, it will produce how many equivalent positions? This is just represent C4. So, I will start with the point here. So, 4mm. So, I will have 2 mirrors. So, when you always combine 2 mirrors, it is always considered 2 perpendicular mirrors. So, like you have this. So, if you have this C4, that means it will come here, it will reflect, then it will come here, it will reflect, it will come here, it will reflect, again it will come here, it will reflect anyway this way, it will come here, again reflection, it will come here, again reflection, it will come here, again reflection. So, you see that, so this is given mirror because you have 2, it is 4mm, but you can see that automatically 2 more mirrors are generated in this. How? So, this also a mirror, it will also get reflected like this. So, again if combination of two symmetry elements produces other symmetry automatically. So, this is one of the examples of that nature. So, like this we can keep on solving several problems. What I would like you to do is you try different combinations of this simple rotation to simple mirror, then inverter, then combination of rotation and inversion, roto inverter, and then rotation plus mirror. So, like that you yourself can combine several point groups and then try to project it on the stereogram like this, and then see how many equivalent points you generate. So, that will be a good exercise. This also will be, this kind of exercise also will be very useful to realize the symmetry in the crystal structures and so on. So, probably I will solve one more problem and then we will stop. So, this is the C3 axis and you have the mirror along Z direction. So, you see here it is slightly different from what you have 4m or which is here it is not the case. Here you see you have this 120, since you have a mirror here it will have reflection, again 120, this you have mirror here it will reflect. So, like that this mirror produces 6 equivalent points, but you can also realize that it generates 2 more mirrors here. So, it is when you say 4m is equal to 4 mm, you cannot say here same here because it is not producing a perpendicular mirror plane, but there is an angle between the mirror. So, you can say that 3 mm is not 3 mm. So, this is very important, 3 m is not equivalent to 3 mm, but on the other hand you have 4 mm is 4 m, 2 m is equal to 2 mm, since it is not producing 2 perpendicular mirror in this operation. So, I will repeat. So, you produce, this is the first point, rotation and there is a mirror, so reflection, rotation, there is a mirror, reflection, rotation, mirror, reflection. So, this things keep on generating this 6 equivalent points for 3 m. Okay, I think one can keep on going ahead with this kind of several explanation or similar point group, space group exercise through stereographic representations. So, I want all of you to try similar exercises and then get back to me if you have any doubt, and you can post your query or doubt. I hope these exercises will be useful in solving some of the assignment problems which we will post. Thank you all.